start talking about the graphs of polynomials. And we've already done that a little bit in talking about the end behavior. We've seen that if I have a non-constant polynomial, okay, constants are kind of special because their end behavior is the same as their behavior everywhere. They're just always at a certain height. But if f of x is not constant, which just means that the degree is 1 or bigger, okay, as x goes off to infinity, f of x is going to go to infinity, or f of x is going to go to negative infinity, just depending on the sign of the lead coefficient. Those are the only two possibilities. F of x is going to get big. It's just a question of whether it gets big and positive or big and negative. Same thing as x goes to negative infinity. F of x is going to either get big and positive, or it's going to go to negative infinity, meaning it's getting big and negative. Okay. But that tells me that unless we're talking about a constant function, which just is a horizontal line, we're going to have no horizontal asymptotes. So we saw a horizontal asymptote in the reciprocal function. If there's a horizontal asymptote, that's saying that my function doesn't go off to plus or minus infinity. It's approaching whatever the y value of that horizontal asymptote is. So it would be approaching some finite number. We're not going to have that. The end behavior is going to be that we're getting big y values. It's just sometimes they're big and positive, and sometimes they're big and negative. So that tells me about the extreme ends of my graph. But what about in the middle? Well, the graph is always going to be continuous and smooth. Now, those are terms that will get formally defined as you work your way through calculus. I'm just going to tell us some things that it rules out. There are no breaks, no cusps, or corners. Okay. Now, a break might be something like so, where my function jumps. Okay. Or it could be something like so, where, oh, there's a big surprise there. Okay. Or it could be something like so, where there's just a gap. There isn't a point anywhere else. None of that is possible. I can tell that we can't have a gap like this. This would correspond to an x value that's not in the domain. The domain for any polynomial is always going to be negative infinity to infinity. Okay. But no breaks tells me I also can't have a break and jump. So there's no sort of unexpected behavior. A cusp would be something like this, and a corner would be something like this. Okay. A cusp is basically when two curved sections come together to give us an abrupt change. And a corner is just when two line segments come together to give us an abrupt change. So a polynomial might change direction. It might be increasing some places and decreasing other places, but it's always going to do that with a nice, smooth, rounded curve. So we won't see any abrupt changes in the behavior like we see when there's a corner or a cusp, something like that. Okay, so that's going to be helpful because we're going to be trying to graph polynomials, and we're not going to get perfect graphs, but what we're going to do is we're going to learn how to calculate certain key points and then play connect the dots. And when we connect the dots, we're not going to do it in such a way that we have any breaks or any corners or any cusps. We're going to have nice, smooth, continuous curves. Okay. All right, so a polynomial could look something like this. Okay, that's a nice, smooth, continuous curve. This one has what I would call 1, 2, 3, 4 turning points. Turning points are just when the function changes direction. We've talked previously about intervals where a function is increasing and decreasing. This one, I guess I can draw in some axes. Okay. This one would be increasing until here, and then it starts decreasing. That's a turning point. We decrease until here, and then we start increasing. That's a turning point. Okay. Now, there's a rule for how many turning points a polynomial function can have. Okay? And if we think about it, the higher the degree is, the more complicated things are going to be. Seems to me like x to the 5th power is a lot more complicated than just x squared. Okay? So the bigger the degree, the more turning points I might expect to have, because that's the more complicated formula for sorts of things. And that really is the rule. If the degree is equal to n, then a polynomial can have, at most, it doesn't have to have this many, but it can have at most n minus 1 turning points. I want to take a look at just two quick examples. If I look at f of x equals x cubed, the degree is equal to 3. There are no turning points because this function is always increasing. It never changes direction. That's okay. If it's degree 3, it can have at most 2 turning points, but it doesn't have to have that many. It's okay to have fewer, but it can't have more. So looking at this graph that had 1, 2, 3, 4 turning points, I know that if that's the graph of a polynomial, it would have to be at least degree 5 in order to get that complicated of a graph. Now, I don't have a full explanation of that rule, but I can suggest why it's true. Let's just take a look at f of x equals x squared minus 4. Now I know exactly what that looks like because that's just my basic parabola translated down 4 units. So this is a function where the degree is 2 and the number of turning points is 1. That would be the vertex. And in fact, every second degree polynomial is going to have a graph that's a parabola, so it's going to have 1 turning point at the vertex. Okay. All right, so how can we get that? Well, what I'm going to do is I'm going to try to find these points here. I can define a 0 of f is an x value that makes f of x 0. So that's very related to the notion of an x-intercept, except that an x-intercept is a point. It's an ordered pair. You've got an x and a y value. A 0 is just the x value. So I can say it's the x value of my x-intercepts. Now, if I wanted to find the zeros of this function, I could say, when is x squared minus 4 going to equal 0? And this one I can factor, because this happens to be a difference of 2 squares. 4 is 2 squared. Anytime I have a difference of 2 squares, I can factor. This would be x plus 2 times x minus 2 would have to equal 0. Just remember why that works out. I'm essentially viewing this as the result of foiling. That x squared, that's my first term. That minus 4, that's my last terms. What happens to the oi? Well, the outsides and the insides are exact opposites, so the outsides and insides cancel out. In fact, that's a very important rule. Anytime you have a difference of 2 squares, it factors as the sum times the difference of the 2 things that you're squaring. Okay, so now if 2 things multiply to give me 0, one of them has to be 0. So either x plus 2 is 0, or x minus 2 is 0. So this would mean x is negative 2, and this would mean x is 2. These are the 2 zeros of this function. Now, if it's degree 2, when I factor it, I can get at most 2 factors that have x's in them. Okay. I could, in theory, have a constant factor, like I could multiply this by 3, and that wouldn't change the degree. But I can't have a third factor with an x in it, because then when I multiplied it out, I'd get a cubic polynomial. So the degree of my polynomial is the maximum number of factors like this. We call these linear factors, because if I just had this function, y equals x plus 2, that would be a linear function. Its graph would be a line. So when the factor is itself a first degree polynomial, we call that a linear factor. If I've got degree 2, I can have at most 2 of those. So I can have at most 2 zeros. Don't have to have that many, but I could have that many. Notice the turning point is in between the x-intercepts, whose location is at the zeros of my function. If I had a function with 3 x-intercepts, so there would be 3 zeros that are the x values of those x-intercepts, it's possible that I could have a turning point in between them. 3 x-intercepts gives me 2 places in between them where I could have my turning points. So that's not a full-on formal proof that this works, but that's an informal explanation about why the degree caps the number of turning points that you can have. Okay, so that's kind of nice. So I know that the lower the degree is, the fewer turning points I will have, so my graph will be a little bit simpler. The higher the degree is, the more turning points I could have. My graph can start to get more complicated. And we're starting to see that these zeros, which are the x values or the locations of my x-intercepts, are going to possibly be some important points on the graph. So we'll talk about exploring that some more in the next video.